All right, let's take a look at number 19, another fluids problem where we're going to be considering this bowling ball when it's half submerged in water here. So what do we have here? A bowling ball has a weight of 72 newtons. And I'll tell you what, right there, let's take that information and turn it into an equation. So the weight of the ball and so we'll continue always in standard units here. The weight of the ball, m times g, mass of the ball times g is 72 newtons. So that's some information. And there was a hint I gave you about fluids problems. Whenever we have fluids problems, if we see a mass, rewrite it as density times volume, all right? Mass equals density times volume. And so the mass of the ball is going to be the density of the ball times the volume of the ball. Actually, this is really what we're trying to find out here, the density of the ball. Unfortunately, we can't solve here because we were not given the volume of the ball. So this is as far as we can go with this. We've got one equation with two unknowns. We do have some more information though. Let's draw on our picture. We're going to have maybe some container of water here. And here's the water level here. And we have the bowling ball half submerged. And it says when it's half submerged, a spring scale, so we're holding that bowling ball up, holding it there and measuring the apparent weight. Remember that a scale can't directly measure the weight of an object, it can only measure the apparent weight. And so that tells us that the scale, we're going to draw on the forces actually on the bowling ball. That's what we're going to do. We're really using Newton's second law in the vertical direction here. We're going to have the scale pulling up, and I'll just write 60 newtons there, okay? You can consider it to be a tension force or a spring force. Anyway, it's 60 newtons up. Now, what other forces do we have? We have the actual weight of the ball, the weight of the ball hasn't changed when we half submerge it in water. It still weighs 72 newtons, but it has a lower apparent weight. It feels a little lighter if we were to hold it there. Which means that our last force, which is the buoyant force, because we have this object partially submerged, the buoyant force has to point upward, and in fact, that's all of our forces. We expect the sum of the forces to be zero, because the object we don't expect it to be accelerating while we're measuring its weight there. And so right away we can conclude that the buoyant force is 12 newtons. And so let's try to use that information. The buoyant force must be 12 newtons in order for them to add up to zero. And so what do we know about, let's start off by writing this. The buoyant force equals 12 newtons. And what's our definition of buoyant force? The buoyant force equals the weight of the displaced fluid, in this case the displaced water. Now weight, we can still write it as m times g. But what m are we talking about? We're talking about it's the weight of the water that had to move out of the way. Right? W there for water. And in our picture, let me just specify here. That's a visualization of the amount of water that had to move out of the way there. So again, we apply our hint here that whenever we see a mass, rewrite that as volume, density times volume. Mass of the water that had to move out of the way, and so that we're going to have the density of the water times the volume of this much water. The volume of this much water, we know some special information about that. The volume of this water is half the volume of the bowling ball. And so at this point, let's take a look at all the things we know and don't know here. We don't know the density of the ball or the volume of the ball. actually we know everything else over in this equation. So in fact, we know the density of water, so we could go in and solve for the volume of the bowling ball and then plug that in over here. Or I guess what I did, either way is perfectly fine. At this point, we've got two equations and two unknowns. The other way that we could do this is just take this whole equation, take this one and divide it by this one, right? Because these two sides are the same, so I could just, divide over by and when I take, this works for me, when I take 72 divided by 12, that'll give me 6 over here. I do get some cancellation. And so what am I going to get? There's a 1/2 down here, so I can write that as 2 times the density of the bowling ball over the density of water. And when we plug this in, we're going to get 3,000.